In the last lecture, we learned that what chemical compound we have is determined both by which elements form it and by the proportions of the numbers of atoms of different elements to each other. But how does one know how many atoms of each element there are in a chemical compound? Atoms are extremely small and clearly impossible to count directly. However, their masses are known and given in the periodic table, typically below the chemical symbol for the element and its name. The masses of individual atoms, or atomic masses, are given in atomic mass units, abbreviated as AMU. One atomic mass unit is equal to 1.660539040 times 10 to the minus 27th power kilograms, and is roughly, though not exactly, the same as the mass of a single proton or neutron. Let's say we have a sample of a known elemental substance. We can weigh this sample to find its mass. Now, if we also know the mass of one atom of the chemical element from which the elemental substance is made, we can find out how many atoms there are in the sample. The mass of the sample is simply the sum of the masses of all individual atoms. Because all atoms of a chemical element are identical, the sum is equal to the number of atoms times the mass of one atom. To express the number of atoms, we divide both sides of this equation by the mass of one atom. The number of atoms is then the mass of the sample divided by the mass of one atom. Of course, we need to take the mass of the sample and the mass of the atom in the same units. Let's say that we wanted to know how many aluminum atoms there are in a soft drink can, assuming that the can is made entirely of aluminum. We could weigh it and find the total mass of aluminum. Say we measured it to be 14.20 grams. From the periodic table, we learned that the atomic mass of aluminum is 26.982 atomic mass units. We can convert this mass to kilograms by multiplying the number of atomic mass units by the value of one atomic mass unit in kilograms, which we know. 26.982 atomic mass units equals to 26.982 times 1.660539040 times 10 to the minus 27th power kilograms. And that equals to 4.4805 times 10 to the minus 26 power kilograms, where we have taken the correct number of significant digits. 1 kilogram is 1,000 grams by definition, so 4.4805 times 10 to the minus 26 power kilograms is 4.4805 times 10 to the minus 26 power times 1,000 grams, and that is 4.4805 times 10 to the minus 23rd power grams. So now we know that our aluminum can has a mass of 14.20 grams. And we know the mass of one aluminum atom in grams as well, 4.4805 times 10 to the minus 23rd power grams. To find the number of aluminum atoms in the can, we divide its total mass by the mass of one atom. So the number of aluminum atoms is 14.20 grams divided by 4.4805 times 10 to the minus 23rd power grams. And that equals to 3.169 times 10 to the 23rd power. So the can is made up of approximately 3.169 times 10 to the 23rd power aluminum atoms. We don't know enough significant digits to be more precise. This number is very large. We often count eggs or roses by the dozen, right? Doing that allows us to reduce the numbers that we state. For instance, instead of saying 36 eggs, we can say 3 dozen eggs. If we want to know how many eggs we actually have, it is easy to find out because we know the conversion factor. 1 dozen of any type of items is 12 items. Of course, anything can be counted by the dozen, including atoms. We could say that 3.169 times 10 to the 23rd power atoms is 3.169 times 10 to the 23rd power divided by 12 dozen atoms, and that is 2.641 times 10 to the 22nd power dozen atoms. However, it is still a very large number. Even counting atoms by the 100, 1,000, million, or even billion would result in very large numbers. 3.169 times 10 to the 23rd power atoms is 3.169 times 10 to the 23rd power divided by 10 to the 9th power atoms to a billion, and that is 3.169 times 10 to the 14th power billion atoms. Still a very large number. So it is practical to count atoms in yet larger units, and the unit that is commonly used in chemistry is the mole. 1 mole is defined as 6.02214129 times 10 to the 23rd power objects. The number of items in a mole is known as Avogadro's number, in honor of Italian physicist Amedeo Avogadro. 3.169 times 10 to the 23rd power aluminum atoms then is 3.169 times 10 to the 23rd power atoms divided by the number of atoms to a mole, Avogadro's number, and that turns out to give us 0.5262 moles of atoms. Or, in scientific notation, 5.262 times 10 to the minus first power moles of atoms. The number of atoms in moles for the amounts of chemicals that we commonly deal with in a lab is usually of the order of 1 mole, or perhaps a few tenths or a few hundreds to a few tens or hundreds of moles. Numbers of such order of magnitude are convenient for using calculations. But why would we specifically define 1 mole as 6.02214129 times 10 to the 23rd power items? Not some other number of a similar order of magnitude, say simply 10 to the 23rd or 10 to the 24th power items. To understand that, let's calculate the mass of 1 mole of aluminum atoms. This mass will be equal to the number of aluminum atoms in 1 mole times the mass of 1 aluminum atom. So Avogadro's number times the mass of 1 aluminum atom in grams that we have calculated, 4.4805 times 10 to the minus 23rd power grams per atom. And when we do the multiplication, we find that it equals to 26.982 grams per mole. When we compare this number to the atomic mass of aluminum that is found in the periodic table, we see that the numerical value is the same. Therefore, if 1 aluminum atom has a mass of 26.982 atomic mass unit, then 1 mole of aluminum atoms will have a mass of 26.982 grams. The mass of 1 mole of atoms of an element is called the molar mass of that element. It turns out that for all elements in the periodic table, the numerical value of the atomic mass of the element in atomic mass units is the same as the numerical value of the molar mass of the element in grams per mole of the element's atoms. Therefore, by defining the number of items in 1 mole as we did as Avogadro's number, we made it possible to find out the mass of 1 mole of atoms in grams simply by consulting the periodic table.